This is the Chapter 2, Lesson 1 video on describing location in a distribution and relative to its distribution. So we looked at data and how to describe a data set in Chapter 1 and comparing two data sets including shape, outlier, center, and spread. Now we're going to look at comparing data to its own distribution. And some of this plays into like the IQR, where we looked at measures of spread. So percentiles are quite related, because Q1 was the 25th percentile, the median is the 50th percentile, Q3 is the 75th percentile, and then our max would be the 99th percentile. So percentile describes the percent of data that a value is greater than. So on a test score, if you test in the 90th percentile, then you did better than 90% of other test takers. So percentiles are important to understand. It tells you what percent of the data a value is greater than, so it gives you a good idea of its position. If it's above 50%, you know it's greater than the median. If it's below 50%, you know it's less than the median. You can also use the other quartiles, the 25th percentile and the 75th percentile, to see where it is relative to those points. So one way we can graph this is cumulative relative frequency graphs. So basically what they are the values on the x-axis, and then the percentile is graphed on the y-axis. So it's another way to see how much data is in certain portions of our distribution. So instead of having a histogram where we see the counts that are in each area up here, here we have the values. So these are old faithful eruptions, their duration in minutes. So our values of interest in our distribution are always on the x-axis. That's what this has in common with histograms and with dot plots. However, now on the y-axis, instead of counts, we have cumulative eruption proportion. So you know the final point on this will always be just below 100%, and the first point would be in the 0th percentile, because 0% of data is less than it. This lets me know that an eruption that's 3 minutes long is just at about the 38th percentile, or 0.38. So you find the value, and then you can find the percentile, so where it lies in the distribution. If I wanted to find the 50th percentile, it'd be right about there, going straight over. Somewhere around 4 minutes. Maybe to me it's looking like a little above 4 minutes. And again, when this has a steeper slope, that means more values lie in there, because there's more percent of the data in there. A smaller slope, we know that there's a smaller percentage of our data within that duration. So here between 2 and just under 2.5, we have a good amount of data. Here we might have the most, somewhere in this range is the steepest slope. So a lot of our data lies here in between 4 and maybe just under 5 minutes. Not much data here, between 2.5 to 3.5 minutes, very little data. So again, the highest point would get to 100%, or all of the data being below it. No value can actually be the 100th percentile, because we're looking at the percent of data that is less than it. So you see your values of interest here, and then the percentile corresponding there. One other way to measure where something is using the mean and standard deviation. So keep in mind, this symbol means the mean, this symbol means the standard deviation. Now if a curve looks bell-shaped and it's perfectly symmetrical like this, we call it normal with a capital N. A normal curve will be bell-shaped, it will be perfectly symmetrical. It's very important for a number of reasons, because we can learn a lot about the curve. Right here where the slope stops getting as steep, so it's kind of getting steeper, 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 it's the steepest value. 68% of our data lie within one standard deviation above the mean and one below the mean. Because of this shape, we can use this, and in symmetry, we can use the standard deviation to say what percent of data are in a certain area. If we go the mean plus 2 standard deviations, which is what this symbol means, and the mean minus 2 standard deviations, which is what this symbol means, 95% of our data lie within these points on the curve. So that would include these two side parts. That's 95% of our data. And then 99.7% of our data, almost all of it, is the mean minus 3 standard deviations to the mean plus 3 standard deviations. So almost all of our data will be within 3 standard deviations of the mean. Now this number 3 is a z-score. It tells you how many standard deviations a value is above the mean if it's positive, or below the mean if it's negative. Values above positive 3 and below negative 3 are very rare, as most of our data lies within 3 standard deviations. So this red portion of the curve, 68% of the data lies within 1 standard deviation above the mean and 1 standard deviation below the mean. When you add in these chunks on the side, That's 95% of our curve, or the area under the curve. 95% of our distribution lies within 2 standard deviations. And then when we add in this final little part to here, just not including this tiny piece of the tail on either side, 99.7% of our data falls within 3 standard deviations. Because we're looking at how many standard deviations something is below or above the mean, we're going to first subtract the value from the mean, and then we're going to divide it by the standard deviation. So we take our value of interest, we subtract the mean, and then define how many standard deviations it is above or below. We divide by the standard deviation. We call that a z-score. So if we scroll down to our graph, the z-score right here would be -3, or 3 standard deviations below the mean. So here we have z-score of +1, 1 standard deviation above the mean, z-score of 2, 2 standard deviations above the mean, z-score of 3, 3 standard deviations above the mean. Conversely, on the other side, we have a z-score of -1, 1 standard deviation below the mean, z-score of -2, 2 standard deviations below, and a z-score of -3, 3 standard deviations below. So that's the formula for how we calculate it. We get a good conceptual idea of what we're talking about. We're trying to figure out how many standard deviations a value is from the mean. Because we're looking at mean and standard deviation, this only works with symmetrical curves, only works with normal curves. The 68, 95, 99.7 rule is what we call that, and it works when things are approximately normal. Now, those numbers are approximations. They're not exact, but they're the approximations we generally use. So here's an example. Let's say my mean is 80, and the value I'm looking at is 93. In my data set, my standard deviation is 6.07. I subtract my value from the mean, so 93 minus 80 is 13. So my value is above the mean, so I know it's going to be a positive z-score. Then I divide 13 by the standard deviation, so I get 2.14. So we'd say that the test score is 2.14 standard deviations above the mean for the data set. So z-score of 2.14 means that. That means our value is just about right there on our graph. Let's look at transformations, data transformations. So if we add a constant to every value in a data set, so let's call our constant A, it adds measures of center and location. So it adds that value to the mean. So if I add a number A to every value in a distribution, then the mean gets that number added to it too. Also the median, because the median would be added to that. Quartiles would also get those, and the values of the percentiles would also be increased by that much. However, keep in mind that the percentile for each point would stay the same, because all of them get added. So if I added 1 to every number, then I'd add 1 to all these measures of center. Now, because it's added to everything, just picture the curve shifting right for a positive number or shifting left for a negative number. So the spread isn't changed. The minimum gets added 1, the maximum gets added 1. The range, IQR, standard deviation. So adding only changes measures of center and location, but not measures of spread. Multiplying or dividing changes measures of center and location. So we'd multiply by the mean by whatever constant b that we're multiplying each data point by, the medians and the quartiles, and the values of the percentiles. However, it divides the measures of the spread by the absolute value of b. If we're dividing by a constant, we would divide those measures of spread. If we're multiplying by a constant, we're multiplying those measures of spread. So if my standard deviation was 3 and I multiplied every number by a constant 2, then I'd multiply my range, IQR, standard deviation, all by the number 2. So keep in mind those rules if we transform a data set. So if we apply these transformations to z-scores, when we calculate a z-score, we're subtracting from the mean, so we're subtracting and we're dividing. So that means the shape overall would be the same as the original distribution, so any skew, any symmetry, but the center will always be 0, since the mean is 0 standard deviations away from itself. We're subtracting the mean and then dividing by the standard deviation, so the mean minus itself equals 0, so our center is going to be 0. So z-scores will always be centered around 0. The spread, since we divide by the standard deviation, our spread will always be 1, or the standard deviation will always be 1 for any z-scores, because any number divided by itself equals 1. Okay, here's your multiple choice. What is the z-score for a value of 25 that is taken from a distribution that has a mean of 22 and a standard deviation of 1.5? So go back through the video, check out the value for the formula for a z-score, and then think in your mind, how would you describe that value? Would it be positive or negative? What does that mean in terms of on which side of the mean it is, the right or the left? So pause now and answer the question. Okay, our last bit of the video is just talking about quantitative data. So anytime you have data, always use a graph of some sort. We've looked at dot plots, stem plots, histograms. Box plots are also helpful. Look for overall shape. So SOX, shape, outlier, center, and spread. 5-number summary and box plot. And when we get a curve that looks like this, or a histogram that looks like this, we would call this approximately normal. Picture tracing over this with a curve like that. We'd call this a density curve. Density curves are always above the horizontal axis. They have a total area under the curve equal to 1, or 100% of the values. And it describes the overall pattern of a distribution. So the area under the curve is, so I could take any two values and look at that area between those values under the curve, and that's the percentage of values in that range. The area under the curve is the proportion of all values in that interval. The median would be the 50th percentile, so it would evenly divide the curve into two equal areas, the left and right side. And the mean, you could picture balancing it on a small triangle, and wherever the curve would balance would be the mean. So on a normal curve, you would have both of those right in the middle, because it would balance in the middle, and that would evenly divide both sides of the curve. So here we have a density curve about the length of hospital stays and the frequency with which they occur. This is relative frequency since it's a percent. We can see we have an overall shape that's skewed right. Skewed right means this mean is pulled away from the median. The curve would balance here if we put a triangle under it or balanced it on a small point. However, the median would divide the curve into two equal areas. And what that's really showing us is that this tail, or potential outliers, or numbers far from the center have an effect on the mean, much more so than the median. My mode would be where the peak is. And here's just a little visual on the balance point and what we mean by that. It's where it would balance evenly, the mean. And you can see the median would be further down here. So here's your free response. Feel free to use your outline and your vocab, which are posted in Schoology. Also read over the summary in your book and look at some examples in Chapter 2, Lesson 1. What is a cumulative relative frequency graph, and how does it let us know where a value lies relative to a distribution? Make sure you include percentile, what it is and how we locate it on there, and also the amount of data that lies within a certain range, what we can tell by the shape of the overall graph itself.